Okay, good morning, everybody. I'm Mary Salvania from KAUST. I will be presenting our work during my PhD entitled Parallel Spacetime Likelihood Optimization for Air Pollution Prediction on Large-Scale Systems. Here we have a movie showing an early sequence of spatial images of particulate matter concentrations over the Middle East and United States. Particulate matter are solid particles or liquid droplets that remain suspended in the atmosphere. The plots exhibit some spatial patterns such that the measurements at any spatial location are related to some degree to its neighbors. We also see some significant temporal characteristics such that as we move forward in time, there is a general movement from north to south. The measurements at any time points are also related to some degree to the previous time points. For spacetime processes such as this, often we want to make scientific inferences and forecast future concentration levels. One way to do so is to use computational physical models such as pollutant dispersion models. However, those models require a lot of assumed inputs such as values of physical parameters and boundary conditions that non-users may find very hard to supply. Alternative would be to use data-driven models, one of which is the class of spacetime geostatistical models. Those models try to understand the dependence in space, in time, and also across different types of data by seeking correlations, and they are suitable for most spacetime phenomena. There are challenges, however, to spacetime geostatistics modeling. These are the cubic growth in computation complexity and quadratic increase in storage complexity with the number of spacetime locations. I will show in this presentation how these problems are addressable through multi-level parallelism using asynchronous execution of computational tasks. Here is the rest of the presentation. I will go through some preliminaries of spacetime geostatistics modeling. I will outline our contributions. I will present our two-level parallelization framework. I will discuss some results and some analysis, and then I will summarize. Here is the setup of our model. Suppose we have a vector of measurements from n1 sampled spacetime locations, where each component is a measurement at a sampled spacetime location st. And we have another vector of missing measurements, and we want to predict the values of this missing measurement vector. Our model requires that Z1 and Z2 are jointly Gaussian, meaning we can write it in this form, where we have mean vectors mu1, mu2, covariance matrices sigma 1, 1, sigma 2, 2, and a cross-covariance matrix between the given and the missing vector. Prediction for Z2 can be performed using the concept of conditional distribution of Gaussian processes. This means that the best prediction for the missing measurements vector, which we denote Z2 hat, can be found using this formula. From the formula, you can see that prediction relies on the mean vectors and covariance matrices. In practice, mean vectors and covariance matrices are estimated from the given measurements Z1. This is done by choosing and fitting a parametric mean function and a parametric covariance function to the data. Throughout our work, we suppose that the mean vectors are the zero vector, so that we can just focus on the covariance matrices. To model the covariance matrices, sigma 1, 1, sigma 2, 2, and sigma 1, 2, we need a parametric spacetime covariance function, which we denote C, with arguments S1, S2, T1, T2, parameterized by the vector theta. This covariance function propagates the entries of the covariance matrices, and it describes the strength of dependence of the measurements at any two spacetime locations. Generally, when the locations are closer, this covariance should be greater than when they are farther apart, in space or in time. A popular spacetime covariance function was proposed by Knighting, and it looks like this, where we see a vector h, which is the separation vector in space, and a separation in time. We see here the script m, which is the univariate Matern correlation function with 6 parameters: a variance parameter, smoothness parameters in space and time, range parameters in space and time, and a spacetime interaction parameter. When beta is equal to 0, we call it a separable model. when beta is greater than 0, it's a non-separable model. We simulate from the non-separable and separable versions of the model. Here we have some examples. You can see at time equals 1, the two fields are identical to each other, but they progress differently as we move forward in time. The non-separable model is considered more flexible as it contains a separable model as a special case. The parameters of the spacetime covariance function can be estimated by maximizing the Gaussian log likelihood function. And this is where the grand challenge in large-scale Gaussian geostatistical modeling lies. It is in the inversion of a covariance matrix. It is where us statisticians are rendered helpless when we encounter a covariance matrix that is very large. And this is where high-performance computing comes to rescue. A C-based software called ExaGeostat was developed for high-performance computing on many core systems that uses tile-based linear algebra libraries to parallelize the core operations on the Gaussian log likelihood function. ExaGeostat depends on various software libraries. MLE is performed using the NLOPT library. The linear algebra operations are done by Chameleon and Hikma. These are tile-based high-performance linear algebra libraries that rely on task parallel programming models instead of the less efficient block-based algorithms. We have then the dynamic runtime system, which deploys the task across various hardware resources. Hikma is the hierarchical approximation version of Chameleon. Chameleon improved the traditional bulk synchronous programming of LAPACK. The default paradigm behind LAPACK is the column major data layout format, while the tile-based algorithms, on the other hand, splits the matrix into small tiles rather than tall panels. The numerical algorithm behind Chameleon can be translated as a directed acyclical graph, where the nodes are the task and the edges are data dependencies. This is an example of a DAG to perform Cholesky factorization. Further scalability can be obtained when we parallelize the maximum likelihood estimation, and this can be done using the particle swarm optimization. PSO starts with a group of potential solutions, each with velocity, such that at each iteration, each one of them looks for the global solution. PSO is conceptually easy and compatible with parallelization. I will show later on how we incorporated PSO to ExaGeostat. For our contributions, we have the implementation of a high-performance spacetime model on large-scale systems, the visualization of spacetime random fields generated by the high-performance implementation, incorporation of the PSO algorithm to the MLE operation to utilize the execution performance in distributed environments. Then we have the illustration of the benefits of a flexible versus simple spacetime model and an application to real data sets. Here is our proposed two-level parallelization framework. For our parallel optimization strategy, we require three things. First, the MPI-COM world, which is the MPI default communicator. We also need the MPI-COM split function, which partitions the default communicator into disjoint subgroups associated with different subcommunicators. And then we need the PP-swarm algorithm, which is the parallel implementation of the PSO algorithm. In a nutshell, we split the default communicator into a set of subcommunicators where each can be used to evaluate a single log likelihood function solution. Here is a depiction of our proposed framework. Assuming we have 32 nodes, the MPI-COM split function will partition the default communicator into 8 disjoint subcommunicators, where each subcommunicator contains the nodes that will internally communicate to evaluate a single MLE solution. In this way, we can evaluate several log likelihoods together in parallel. We test our proposal on synthetic and real data sets, and it's tested on an Intel-based Cray XC40 system with more than 6,000 compute nodes, and all experiments were conducted in a whole number of cores with different nodes. First, we show the advantages of using a more sophisticated, non-separable model over a simpler model. Generally, modelers would prefer a simpler model because there's less number of parameters, and generally it takes less time to find a solution. However, we see here that doing so, you actually lose some accuracy, and with our implementation, you don't have to choose one over the other. You can go for the more flexible one, and you can still do the computations. Here we have the box plots of the prediction errors when we fit a separable and non-separable model on spacetime data with varying degrees of spacetime dependencies. We can see that if the data comes from weak spacetime interaction, the two models perform at par. And the difference appears when we are under the moderate and strong scenarios, when the separable model can no longer capture the non-negligible spacetime interaction. Next, we see that our implementation is able to recover the true parameter models. Here we have the box plots of parameter estimates under varying degrees of spacetime dependence. The true parameters are highlighted in red. We can see that the medians match the true parameter values. Next, we move on to the real data. Here we have the log PM2.5 over Saudi Arabia. We expect to see strong correlations in space because we see huge spots of red, yellow, and blue. But we also expect weak correlation in time because the spatial images are substantially different from one point to the next. Next, we also have the data from the US. And similarly, we expect strong correlations over space, but this time we may expect some strong correlations in time as we see the spatial structure persist even after the 20th time point. Here we summarize the values of our estimated parameters and also the errors. We prepared two testing data sets. For testing data set 1, we randomly remove measurements within the time frame that we're considering. For testing data set 2, we will forecast on all locations 2 time points ahead. We can see that generally, non-separable model reports lower prediction errors, although the difference are small because the numbers that we are predicting are also small. In order for us to see if there's really a difference, we do a pseudo cross-validation study on the testing data sets where we only forecast and predict on subsets of the testing data sets. And as we can see from the box plots, that generally non-separable models report smaller errors than the separable models. Next, we move on to the performance of our proposed implementation. Here we have the performance of a single MLE optimization step using different number of nodes on the Shaheen 2 supercomputer. Each bar represents the work distributions, where the first number is the number of subcommunicators and the second number the number of nodes per subcommunicator. We can see that the best performance is obtained when we use the smallest number of nodes per subcommunicator that can handle a given problem size. For example, figure A, when we have 128 nodes, the performance when we use 8 subcommunicators with 16 nodes is 6x more than when we use a single communicator with all the 128 nodes. That is for a 40,000 by 40,000 matrix. Similar pattern can be observed when we perform on 160,000 by 160,000 matrix. Next, we see the performance of one MLE optimization step of one level, which is the default in the XGSDOT, and our proposed 2-level parallelization. The red box is the theoretical peak performance that can be achieved by a certain number of nodes. When we use one-level parallelization, you can see that the performance actually degrades when we increase the number of nodes for smaller problem sizes. It's because there's not a lot of work to keep the nodes busy. But the 2-level parallelization shows some scalability, so if you increase the number of nodes, the performance also improves. Here we see the boost in performance when we use 2-level parallelization over the 1-level parallelization. If you look at the 490,000 by 490,000 covariance matrix, we have a 3x performance when we do our proposed method over the 1-level parallelization. Next, we have the time to solution of one MLE operation, of the full MLE operation using 100 optimization iterations on the Shaheen 2 supercomputer for 1-level and 2-level parallelization. As you can see, when you do 1 level, there is a point where adding more nodes no longer improve the time to solution. For example, in figure A, going from 256 to 512 no longer decreases the execution time. And so if you look at the pattern for 2-level parallelization, it actually keeps the scalability in terms of execution time. And also when you go from 512 nodes to 1024 nodes, you actually decrease the execution time. We also see in this figure the speed up if we double the number of nodes. For one level parallelization, you can see that we don't really reach the theoretical speed up. When you double the number of nodes, you actually should want to double the execution time, also the speed up. But you don't have that in one level parallelization, and you actually see that in our proposed framework. To summarize, we propose a two-level parallelization framework of geostatistical spacetime modeling. At the upper level, we have subcommunicators performing the independent log likelihood function evaluation with different sets of parameters via the parallel PSO algorithm. At the inner level, we have the task-based parallel technique used to perform linear solver operations on a given set of nodes representing a single MPI subcommunicator. We demonstrated through synthetic and real data sets the merits of our proposed implementation, and we achieve high prediction accuracy with up to 757 T-flops using 1,024 nodes on the KAUST supercomputer. Our other avenues for further research include Tylo rank and mixed precision approximations to accelerate further the modeling process. Here are the references, and this work appears in the ACM Platform for Advanced Scientific Computing Conference proceedings. So that is all. I'm ready for questions.
Thank you very much. I think we have enough time for questions and comments. Anyone interested? Yeah, please.
So I'm Martin from UT Austin. So I wonder in what context would I be interested in, so we just heard about like Beck approximations and different, just one type of Gaussian approximation. So in what context would I be interested in using this parallel method you presented over using just a Gaussian plus approximation, which seemed, as the colleague said, seems to work pretty well. What are the advantages, I guess, of the approach?
So this one is using dense computation, so we don't make approximations in the covariance matrix. That is helpful when, even at far distances in space, the correlation does not decrease. So if you have intense correlation, even at like 10 kilometers, and your covariance matrix is 1,000,000 by 1,000,000, and even at the 1,000,000th farthest point, your correlation is not even close to zero, then you will lose some information if you do some approximations.
Sure, yeah, actually. Did you guys compare maybe your approach to, like, say, the Beck approximation, or was that part of your study too? Like, how do, for example, for a given time or given amount of computing, the precision in both?
Yeah, we didn't do it here, but we have approximation versions of this framework in some other papers from our group.
Anyone else?
Yeah.
So just wondering, like, how big are your data set and data sets, and I guess how long does it take to execute? Like, I think that my supercomputer is probably not as good as your supercomputer. So, like, how long would it take me to do it on my supercomputer kind of thing?
Yeah, it depends on the performance of the hardware resources. But technically, in my experience, the usual is 1.5 hours to find the solution of a 500,000 by 500,000 covariance matrix. So that's like using, I forgot how many, but it's just a moderate number of nodes. So if you can use more nodes, then you can do less than an hour.
Thank you. Anyone else? Actually, I want to ask a question.
Okay.
I saw you're using two applications, Saudi Arabia and Midwest US. Do you try the whole US data or just the part of the US data?
Yeah, it's just that area because we want to make sure it's stationary. Because if you do other regions, then you might have like mountains and, plain fields, so it's non-stationary.
Okay.